So welcome to the week 10 of the live sessions on the NPTEL course Introduction to Electrical Engineering, and I hope you can see my screen and my voice is also clear, right? So as already told, we'll be discussing and solving problems on induction machine, both three-phase and single-phase. I think the slides are also moving, right? Okay. So we have an extra session on 12th of April. Please join that session also. We have more, that is, we are in the week 10. Apart from this, two more regular sessions will be held, 11 and 12, and plus one extra session, right? So every day, on Tuesdays we have the weekly sessions, and next 2 weeks also we'll be having on the same time and same day of that weeks, we have two sessions, regular sessions, but one also extra session on 12th, right? Please note, Saturday, 10 a.m. to 12 p.m. So we'll be briefly covering through many things and magnetic circuits and transformers and part of some other concepts also we'll be discussing. So that is an extra session that I already placed, and I request you to join that session. That will be helpful, okay? For your exams, which are scheduled on 27th of April, right? So we'll finish much before that, and hopefully everything will be done from this side, from the problem solving part. And today's discussion will be on induction machines, right? Both three phase and single phase. So without any delay, we can start, I think, because we have to go with the time. So any doubts? If any doubt, you can just let me know. Any doubts you face till now? Just feel free to stop me anywhere if you face any doubt, right? Otherwise, we can go ahead with today's content, right? You are able to hear me, right? Okay, so if you don't have any doubt, we'll just start with the three phase. Now, three phase induction machine, I think you are well aware how it works and on which principle it works. Actually, it is a singly excited machine. You know singly excited and doubly excited machines? Any answer? Please be interactive because it will be helpful for you, right? So what we call a singly excited machine and doubly excited machine are that where you have two energizing circuits, right? Like in synchronous machine, if you know, okay, if you don't know also, okay, right? Because we'll cover synchronous machines because these are basic electrical course. In synchronous machine, see what is how a rotating machine works is basically we have two magnets like this, S and N, I can say. So two magnets, one rotating magnet and the other magnet trying to catch it. Because if you have some magnets like this, and I place a magnet like this. Now, what will it try to do? The S pole will try to be attracted towards the N pole, and N will try to attract towards S. But what if I purposefully somehow make an arrangement to move it further by some external energy, some force I apply? And again, when it tries to catch that other magnet, which is free to rotate, or you can call it the rotor, I forcefully or purposefully proceed or move it ahead by some external means, which I call as mechanical energy. If you think like that, then it will try to catch it, right? That is the purpose of machines, where you have purposefully created one magnet and one free to rotate body, right? So you must know that magnets attract magnets, and also ferromagnetic materials, that is, which are not magnets, that also are getting attracted, right? Sorry, ferromagnetic materials, right? which freely allows or easily allows passing of magnetic fields. Those materials also are attracted towards magnets, right? Like iron or other things. So if you also place an iron also near the magnet, it will try to be attracted, right? Like for example, you have a magnet like this, and you have a piece of iron like this, and you force it along a path, right? A hinge. So what the iron will do? Try to align with the magnet like this, because magnetic flux lines are easier to pass through a aligned path rather than an unaligned path, because it has to traverse more, right? So it will try to align it with the field, like completely aligned with the field, because it induces a form of some N and S poles. Some kind of induction happens, alignment of the dipoles you can also tell, and it tries to align it. So that's how a machine also works. A induction machine, we call it a singly excited machine because you have the stator. Unlike DC machine, the stator or the armature circuit, the stator is itself the armature circuit, right? Where you have A, B, and C, three phase coils. Not one, we are symbolizing it by one, but there are many coils. But one coil combination forms A phase, right? But there are many distributed coils, as you can understand. Why we will just explain. So A dash, then B, B dash, and C, C dash. We are drawing it. See, this representation means that there is a coil like this, which is entering like this and coming out like this over the armature. Armature is a big slotted body, right? Iron body. So you place one conductor on one slot, and the return conductor also is placed on the diametrically opposite slot. That's why diametrically opposite. So these are the paths. But there are not one coil which are responsible for one phase. Many such coils distributed together over the body of the machine for mechanical purpose as well as electrical purpose are being generated. So that's why so we'll discuss, okay? But for the time being, understand that the power circuit or the armature circuit, which in the DC machine sits on the rotor, is now sitting on the stator. Stator is the static body, right? We symbolize it by this, like up this symbol. So the stator itself is connected to the power source if you are connecting or trying to operate it as a motor, or we need to tap out the power from the stator itself if you are trying to operate it as a generator. But for an induction machine, please understand, or a synchronous machine, stator composition, stator, I can say, configuration or how you make the stator, that remains the same. Stator is what? It is a slotted structure where you place conductors of all the phases, right? So conductors are connected accordingly. For each phase, you have a dedicated series of slots where you place the conductors, distributed conductors, and accordingly you tap the windings out. So that is how you make or construct the stator windings for these kind of machines, which rotates on the principle of rotating magnetic field. Just we will discuss how. But please understand that what is a singly excited machine then? Then we have one energizing circuit, which is the stator itself for an induction machine. Because what is there in the rotor? In the rotor, you have simply bar-like structures which are placed like this. And you connect the end rings, right? So there are aluminum bars and you connect them, the end rings, together to short the coils and make a kind of squirrel cage configuration. So this is the rotor, right? This is a rotor structure, but you are not energizing the rotor. So it is becoming a singly excited machine. You are only exciting or energizing one circuit, which is the stator circuit. Unlike in the synchronous machine, which we will learn that we have two energizing circuits, one stator, one rotor. So can you tell me who is producing the field here? Just arbitrarily, who is producing the field? Just like you see in DC machine we discussed in previous week, we have a field circuit and we have an armature circuit. Armature circuit sits on the rotor itself in the DC machine. But in the AC machine, who produces the field or who handles the power is the same person. Who is that person? He is the stator. Stator has coils. You plug in with the power source, the three-phase balanced power source, and it creates or generates the field. How? We'll see. But please know it creates the field, as well as the stator also handles the power. Power means the load, it provides for the load. If it is a motor, it takes the power. If it is a generator, it gives the power. But the power is also handled by the same person, which is the stator, as well as the field. Field is produced also by the stator. Rotor does nothing, but what does the rotor we need for then? If rotor is for nothing, if it is not creating the field, neither it is handling the power, then what for we need the rotor? Any idea? Field is also created by stator. Power is also handled by stator. So what for the rotor is correct? See, rotor is nothing connected to the shaft and it rotates the load. That is a purpose. Okay. But what else it is doing? Absolutely correct that rotor is there to take the load, the shaft load. For the any motor, it is true, right? You will, even if it is a DC motor also, rotor is the armature, right? But it has to take the load with the shaft. So the rotating part here is called the rotor, but the rotor is not energized. Please understand. It has to take the load, okay? But is the rotor doing anything else? I just told you the concept of magnets. Any rotating machine, purposefully you have to create virtually two magnets, one on the rotor, one on the stator. If it is not so, how can it rotate? I told you, one moving magnet and one magnet has to catch it, like a donkey and a carrot. The carrot moves forward, the donkey continuously tries to trace it. So long as you carry the carrot forward, the donkey will move. Similarly, so long as you withheld by external means the rotating field, a virtual rotating magnet like this, which is rotating in space, if you can virtually create that magnet which is rotating in space virtually, then only the rotor can track it or rotate with it. So even if the rotor, there you cannot see any magnets by eye, because actually there is no magnet in the rotor for an induction machine. But virtually there is magnet getting induced because of Lenz law. What the Lenz law says? That if you cut the magnetic field lines on a conductor, it generates EMF. And once it generates EMF, since the rotor is shorted, it carries current. And once it carries current, it will generate poles because it generates flux lines. Virtually, it will generate poles, which tries to oppose the main flux. We discussed all these things, that what Lenz law says. But the basic fundamental philosophy of Lenz law is that whatever is creating that thing, the resultant thing will try to oppose that thing in the same dimension. So what was the source? I plugged into the power source. Somehow it created some field, some magnetic field virtually, which is rotating in space like a moving magnet. It is rotating in space. That, due to Lenz law, did what? Created cutting flux lines on the conductor, on the shorted conductor of the rotors, which itself generated a EMF, which produced currents, which produced flux that tries to oppose the main flux. How can it do? By revolving, by rotating. Because what was the reason that the flux lines were cutting the rotor? What was the main reason? Due to the virtual rotation of the magnet. Now, since the magnet is virtually rotating, what the rotor currents or rotor current produce flux wants? That there should not be any flux. Because earlier the rotor was sitting with no flux. You plugged in the power source that generated the rotating magnetic field. The rotor will produce currents, or the rotor currents will produce flux so as to oppose the main flux. How can it do so? Because the magnet is rotating, right? It cannot just produce a magnet in space which is not rotating. If it does so, then it cannot oppose the main rotating magnetic field. So, in order to oppose that main rotating magnetic field for which the rotor got the induced EMF or the currents, the rotor has to also rotate. And virtually induced magnetic fields does what? They try to oppose the main flux. So that is a way, Lenz law, it is just a Lenz law, that the rotating magnetic field will be opposed by the rotor by the rotation of the rotor. And the rotor will virtually get induced EMFs and produce poles, fictitious poles. And you know that for rotating machine, the generalized theory of rotation, what does it say? That to get continuous rotation, stator and rotor MMF needs to be stationary in space with respect to each other. And the number of stator poles and the rotor poles should be same. Stator and rotor poles need not be existing practically, but virtually I am telling. So virtual number of stator poles should be equal to number of induced rotor poles. Because actually there are no poles on the rotor, but rotor poles will get induced in order to oppose the main rotating. That is also virtually created stator pole, right? Stator poles are also virtually created, rotor poles are also here virtually created, because in induction machine you cannot see any poles with eyes, because everything is virtually created by mathematics. How? We just see. So just see this animation. So we have the coils which are mechanically displaced by 120 degree. Just you can see in this diagram, they are mechanically displaced, and within that coil you pass three-phase voltages. You just apply three-phase time displaced voltages. So space displaced coils getting time displaced voltages. What it will do? It will produce a MMF or a flux or a pole, whatever you want to tell, a kind of virtual magnet which is rotating in space, and that strength of the magnet will be constant. It will not vary with speed, neither vary with the rotation or the position of the rotor. Whatever position is the rotor rotating, and whatever speed may it be rotate, but for a constant given voltage of fixed particular magnitude, the strength of the magnetic field, whatever you can see here, that strength will be constant. So it produces a, I can say, a very smooth magnet which is not varying its flux or strength with the position of the rotor, and it is rotating also in space. Mechanically it is rotating. Virtually, actually virtually there is no pole, actual pole, but virtually we create a pole that is mechanically rotating, or we say in our language that it is rotating in space, because we have the space displaced coil, but the currents or voltages are displaced in time. They are not given in space, right? So you need to understand space and time. Time means with time the voltages are varying, but the axis is not changing. But what you mean by space, that actually in the body of the stator what is happening. So we, by giving time displaced voltages through space displaced coils, which we name as A phase, B phase and C phase, what we try to do, we try to create a magnet, moving magnet, virtual magnet in space, which we name as the rotating magnetic field. And I told you by Lenz's law, if I apply these voltages, obviously the rotor will try to catch the virtual magnet by Lenz's law, and at initial stage it will get induced voltages because of the cutting of field lines in the stator rotating magnetic field. Whatever magnet was rotating in the stator, that will be cutting the fields in the rotor conductor, and it will get induced EMF. But since the rotor is itself shorted in a squirrel cage machine, what will happen? It will pass currents, and that those currents will flow flux, generate flux, and that flux will try to oppose it. So the rotor will rotate so that it can oppose the main magnet flux, right? That is the basic Lenz's law and how it, the induction machine rotates. So this, you can also see this animation where we have just created the polarity. What is the polarity and how the coils, because polarity is changing, right? You can see the polarity is getting changed. See this, look at these coils. They are continuously increasing and then decreasing. That is how a sinusoid behaves. A phase voltage is increasing and decreasing in A phase coil. B phase voltage is increasing and decreasing because it is a sinusoidal voltage, but not in phase with A. So when A phase is maximum, B and C are negative maximum. So 1, this is minus of minus of. That is how a three phase works. So when A is maximum, B and C are negative half of maximum, voltage wise I am telling, similarly flux wise, and they will group together to form the magnetic field. That is how you can resolve and check by adding the voltages, MMFs, that F of A and f of b and f of c, both of same magnitude, you can add and then get 3 phi by 2, right? Why it is so? Because because A phase was like this, B phase was like this, C phase was like this. But how the flux line with time looks like? When A phase is maximum, B and C are negative half, so it will flip. So when you add them, you will get the flux in one direction only. In any time you add, I told you the flux will be constant. So that's why the flux, field flux, the strength is constant, but it is rotating. And the polarities are varying because it is a time varying sinusoidal signal. The coils will receive time varying voltages, but due to the time variation in the voltages of the coils, the A phase coil, B phase coil, and C phase coil, the flux will be of fixed magnitude. That is the beauty of the system, but it will be rotating in space. So that is how the animation also shows you that how we create a rotating magnetic field. So creation of this animation actually shows you the creation of a rotating magnetic field, right? Creation of RMF. And that is the basic principle behind the rotation. So we say the asynchronous machine. These kinds of machines are asynchronous singly excited machine. So these are asynchronous singly excited machine. I hope you understand what you mean by asynchronous, because once it catches the synchronous speed, the Lenz law will end because it will not again receive the induced voltages. So once rotor catches ns means the synchronous speed. The synchronous speed, once it catches, then what will happen? It will lose the induced EMF and the operation will stop. That's why induction machine can never rotate at synchronous speed. It will try to rotate at very close to synchronous speed, but it can never catch the synchronous speed because asynchronous machines operate by principle of Lenz law. They try to oppose to the maximum possible extent but cannot catch the cause itself. It will try to oppose but not catch the speed itself. So because of the inertia of the rotor, ideally it should rotate at synchronous speed, but due to the inertia of the rotor, the inertia itself creates a load on itself, right? Inertia of the rotor itself creates a load on itself, and it rotates slowly, very close to the synchronous speed at no load, but not exactly at the synchronous speed. That's why we introduce the term slip for asynchronous machines, which is defined by the difference in the rotor speed and stator speed and in per unit. So this is per unit, right? Because we divided by ns. But actually it is nothing but the difference of the two speeds. So once you sit on the rotor, if a person sits on the rotor and tries to observe, then what will he observe? The speed of the rotating field. He will observe that it is ns minus nr, because this magnet is rotating with ns. But if I go and sit on the rotor, what will I observe? That the speed of the magnet, virtual magnet, if I can see it with my eye, then what would I have observed? That ns minus nr. So rotor also sees that a magnet is trying to cut it with ns minus nr speed. Accordingly, the frequency of the voltages induced in the rotor will be slip times the frequency of the stator. As you understand, we call it slip frequency. So frequency of voltage and current in rotor. So the rotor observes a slip frequency. But can you tell me the rotor MMF and stator MMF, are they relative? What is the relative speed? So rotor got some induced voltages and tries to create some currents. Due to that, a flux also comes in space. So I am asking you, what is the relative velocity between stator and rotor MMFs with respect to a stationary frame? Stationary frame means you go and sit on the some stationary frame and try to observe both the fields, right? One is the stator field, one is the rotor field. Rotor field, why it came? Because the rotor was shorted and the rotor got induced EMFs that passed currents that created the MMF. Okay, understood. But what is the speed of the rotor MMF with respect to a stationary frame of reference? It will be also the synchronous speed itself. So rotor MMF also is rotating at the synchronous speed. Why? Because I told you that frequency of the rotor currents or voltages which are creating that field, that rotor MMF, is slip frequency plus the rotor field plus the rotor speed, right? Plus rotor speed. So what is rotor speed? 1 minus s times f times fs. So it will fs or omega s, whatever you call, omega you call, angular wise. So that will also be synchronous speed, right? So we prove that in any frame you go in a rotating frame. In rotating frame, you see both the fields rotating at sleep frequency. In stationary frame, so I write in rotating frame, both fields rotating sleep frequency, SF speed. And in stationary frame, both fields rotating synchronous speed. So from ns you go back to omega s or whatever fs. You know the formula, right? Ns equal to 120 f by p. So a frequency corresponds to a particular speed for a given number of poles, that you know. So that is how we are actually trying to create a kind of system which has a stator MMF and a rotor MMF. Virtually we are creating two magnets, which is essential for the rotation of any machine, and they are also stationary in space with respect to each other, which will generate smooth torque. So stationary in space, stator and rotor MMFs are stationary in space. Stationary in space is a requirement, is a necessary requirement for rotation of any electromechanical system for smooth torque, right? For smooth torque. But just think over a time that how do we actually create those poles? You understand it is a two-pole system, okay, understandable. But how to create four pole? How to create maybe 6 poles? How do we actually create 6 poles on the stator effectively? Can you think and tell me? Just think over a time. Yes, more winding, but how? Can you tell how to connect the windings to create 4 poles or to create 6 poles? Because virtually you give the voltages of the phases like this and it creates a field, okay, like this. But how to create this? I want to create this. How to create it? Just think, just give a thought over it, that how to connect the windings of individual phases to generate such pole pairs. Okay. Okay, that we will get some stationary rotating magnetic field, understood. That concept is understood. But how to increase the number of pole pairs? That is just give a thought over it. Okay. It is important. Okay. Can you tell me how to create, just verbally? A opposite to A1. Just 1 second. I am connecting my charger. Just wait one. A opposite to A1, correct? Then what we will do? You have one coil. Maybe example, for example, let us say 1 second. Yes. What you are telling, you are trying to tell is this, that whatever I told you from the discussion so far, that maybe there is a coil named AA dash, which actually is going like this and coming back like this. So if you pass the current, the flux will be like this. It's a magnet, kind of one magnet which is toggling, right? So then B and B dash and C dash will come and make it a rotating magnet. That concept is understood. But one magnet it will create. Only one magnet it will create. If I try to do like that, okay, I told you coils are, each phase coils are also mechanically displaced. So A, then B, then C, and diametrically opposite will be B dash and C dash. But this system will lead to generation of one pole pair which is rotating in space. Understood up to this? So how will it do? When A is maximum, likewise see the polarity. B and C are in the same orientation, I can say, but negative. So small cross. Understood what I am trying to tell? When A is maximum, B and C are also. When A is maximum, A is sitting here, okay? B and C are reverse of A. That is negative, but small, half of that. So A is here, B and C are what? B and C are like this, B and C. So are dot and dot. But what is happening to B cross and C, B dash and C dash? If dot is there, the cross will be like this. So B dash and C dash are putting the cross. So a group of coils are being created which is responsible for the generation of one pole. So you see the cross sits on top and the dot becomes on bottom. So that is how a flux is created or a virtual magnet is created of constant strength of the strength maybe N and S. But one pole pair is getting generated. What to do in order to increase the number of pole pairs? Can you just think what we can do? Just answer. Just try to give a guess because this is important, right? We see 4-pole induction machines. We see 6-pole, right? And what is the benefit of increasing the number of pole? Why we want more poles? Yes, one more AA1, correct. But where to place that? One more AA1, correct. Where to place that? Where to place that? Mechanically. Where in space should I go and place that? Opposite of A, no. Not opposite of A. Opposite of A dash is sitting, right? Just see this diagram. Everything is hidden in this diagram. If A was here and the magnet was generated like this, where to place another AA1 so that a magnet is generated like this? Ah, correct. That you got the answer, right? So that is what is called as a pole, electrical pole. Electrical pole, the difference between two electrical poles are 180 degree. That's why we tell, na. Mechanically it is 90 degree. That is how it is getting generated. Understood, right? So place another AA1 90 degree, maybe a group of coils. Now answer one of my another question. Now you got the answer. Okay, correct. So place AA1, A dash, A2, A2 dash, another A phase pair which gets excited with same A phase together with that A1, A1 dash, right? So if it has A1, A1 dash and A2, A2 dash. Now why we are talking about all these things? Because it is important to analyze what is going on inside the machine, right? So that's why we talked about this, that how we place another coil which can help in generation of another pair of magnets. Now can we go on doing this? Increasing the number of poles to get more or less speed? Go on doing this? And rotor will go on adjusting itself to the number of poles? Because we told for smooth torque, stator and rotor MMF should be stationary in space with respect to each other. But is there any limitation? No, NS less than N are okay. But what is the constraint that must be imposed? Is there any constraint? I can go on doing like this, increasing number of A2, A3, A3 dash, A4, A4 dash. I can go on increasing the pole pairs, right? But is there any constraint from the rotor side? From the design perspective, rotor side, any constraint? the slots in the rotor should also agree to this. Just like you are plugging in the stator slots, some A phase windings, multiple A phase windings, for that you are generating more pole pairs. The slots in the rotor also should be built in such a way to adjust itself to the number of pole requirements of the stator. Now, if I go on doing this and I exceed the number of slots in the rotor, like I told you, bars are there. If I exceed that, then rotor poles will not be able to adjust itself to that many number of poles. How can it do? Because one may be adjusting, maybe in the first case, when there was only one pole pair, many of the rotor bars group together to create one pole pair, right? Now you increase the number of pole pair. So now group of rotor bars are corresponding to one pole pair, then a group of another rotor bars are corresponding to another number of pole pairs. Initially, many rotor slots were grouping together or grouping themselves to create one pole pair. After you increase the number of pole pairs by putting in multiple phase A coils in the stator, that group of slots in the rotor reduced. Now you can keep on doing this up to you reach that constraint when you are equaling it with the number of rotor slots, because above that the rotor cannot put itself or adjust itself to pass on or make that number of pole pairs. So the number of rotor slots is the constraint to create that number of poles, right? And when I am talking about three-phase system, can you tell me what is the number of phase of the in rotor? Number of poles in the rotor is equal to number of poles in the stator, agreed. But what is the number of phase in the rotor? Can you please tell me? We are talking about number of poles adjustment made by the rotor virtually to equalize it with the number of poles in the stator itself, because of the general theory of rotating machines. By the general theory of rotating machines, stator and rotor MMF should be stationary in space with respect to each other, for which the rotor has the constraint to adjust itself to the number of stator poles. That much understood. But I am telling you, can you tell me about the number of phases in the rotor? The number of phase in the stator is 3. Does the machine theory tell me that it has to equalize it with the number of stator phases? No. It is not 3. Just give it a thought. The machine theory or the general theory of AC machines does not tell me anything about making the number of stator and rotor phases equal. There is no constraint on the number of phases. Even you can take a polyphase induction machine and do something somehow, making the winding connection somehow to create maybe 6 poles. Just we talked about how. And rotor will also adjust itself to 6 poles, and smooth torque, smooth rotation will be achieved. But you don't still know what is the number of phases of the rotor, and I can guarantee you that there is no such constraint that the number of phases of the stator and rotor should be same. In this case, you know how the rotor phases will be. The number of rotor phases, just give it a thought, will be equal to the number of slots per pole. That I told you. The number of slots per pole will be number of phases. Similarly, like the stator, the number of slots per pole will be the number of phases, right? So per pole, how many slots are there? That will be the number of phases. So you see, number of slots per pole in this stator was 3. You see, saw this? One pole pair, now a pole pair, okay? Or one pole you write, because 6 slots, so number of slots per pole I am telling. So under N pole 3, under S pole 3, that was for the stator. Similarly for the rotor also, number of slots per pole. But the number of slots will be more for the rotor, because rotor has many such conductors. That's why I told you the limit is number of slots for the pole adjustment. I told you, na? So that's why each conductor, many slots are there. But let's say 2 poles only. Then what is the number of phases? Number of slots by 2. By 1. because under by 2 you can tell, because number of slots under S pole and N pole will be half. If there are 2 poles, N and S, in the rotor also there should be 2 poles, N and S. Now there are, let's say, 60 slots in the rotor. In the rotor there are 60 slots. Then per pole how many slots? 30 slots per pole. If 2 poles. So there will be 30 phases, right? The rotor will be like 30 phases. Equal to 30 phases, right? That number of phase will reduce as you go on increasing the number of poles. So number of rotor phases is number of slots per pole. So I told you what? That if the rotor has 60 slots and there are only 2 poles in the stator, rotor will also induce 2 poles. Now per pole how many slots are coming? Per pole 30 slots are coming. So 30 phase will be there for the rotor. The rotor conductors will be 30 phase. Can you imagine? For a 3-phase system, there will be 30 phase in the rotor. So the number of poles should be equal, not the number of phases. My concept is clear, right? This you will not find in many books, but it is a concept that many people don't know. And I am here to tell you the things that you don't know, and it will give you interest. So what I was telling is that the number of phases in the stator and rotor. Up to you, this you understand that for smooth rotation for the general theory of AC machine, what it mandates, the stator and rotor pole should be stationary in space with respect to each other. Up to that much you understood. And for that, the number of stator and rotor poles should be equal. Otherwise, you cannot get smooth torque, right? Just give a thought about it, why you cannot get smooth torque. If you have maybe a 4-pole system and maybe a rotor which is having 2 poles, you will not get smooth torque. Just think why. Okay. Otherwise, in the next class, we will just have a discussion on this, that why number of stator and rotor poles needs to be same. In synchronous, we will again touch upon that. But just for the timing, please think, for smooth torque, stator and rotor MMF, equivalent stator and rotor MMF should be stationary in space as well as equal in number. Not equal in strength. Please note, equal in number for smooth torque. So understood that they should be equal in number, and for that, if I have 2 poles on the stator, I should have 2 poles on the rotor. But what I am telling, the stator is 3-phase, that you can also see. And I told you the rotor poles are nothing but number of slots per phase, slots per pole. Now how many poles should be there in the rotor if the stator has 2 poles? 2. Now if there are 60 slots in the rotor body, per pole how many slots you are getting? 30. 30 slots are contributing to N phase, 30 slots are contributing to S phase, just like how the stator did. Similarly, rotor will also create 2 poles. Now under 1 pole, how many slots are coming? That much will be the number of phase. Why you understand, na? Because if there are N conductors and a magnet is rotating, one time it will induce maximum voltage here, one time it will induce maximum voltage here. So all the voltages will be of different phases. That's what we call number of phases, right? So under 1 pole, how many slots are coming at a time? At a time, how many slots are contributing to 1 pole? That's how we call it number of slots per pole. So if there are 2 poles and 60 slots, then 60 by 2, 30 slots under 1 pole, and that will be number of phases. So number of rotor phases are nothing but slots per pole. If there are 2 poles and 60 slots, 30 phase will be there for the rotor, for a 3-phase stator induced induction machine, right? If 3 phase are there in the stator, 30 phase will be there in the rotor. Get my point, right? But the number of poles are still 2. Get my point? Yes. So that's what I wanted to discuss. Okay. So just see this diagram. That's how we create more number of poles, by winding. Similarly, A1, A2, A3, A4. How many number you want, you can increase, right? Only you need to have a concept how to place the poles. It is just like this, by increasing number of windings. As you can see, U winding or A phase winding is going here, and then again it is going here, right? 90 degree. There's 4 pole system. For 4 pole, 360 by 4, 90 degree apart, you create the poles. To create the poles 90 degree apart, A phase should be 90, another coil should be 90, right? 2 you need. So like that you create more poles, right? Just go through the slides, you will get a point. These slides are shared in Drive, you are getting everything in the portal. Just click on that, you will get all the material, right? I hope the concept is embedded, right? No, you cannot see anything with your eye. But the general theory of AC machine tells that it will be induced. You cannot see electricity also with your eyes. You cannot see poles also with your eyes. There is no concept of poles. There are dipoles. If you cut a magnet, N pole, S pole, that will be also N pole, S pole. Can you see N pole, S pole with your eye? No. The effect is just attributed to. But what we are mandating is that to get smooth torque, number of poles should be equal, not number of phases. So why the number of phases are more? Because the number of slots are more for the rotor. Simply because of this reason. The rotor has more slots. So that many slots coming under one pole is attributing to that many number of phases. Because one pole under one coil will create a voltage that is different from the coil just sitting adjacent to it. Get my point? That is the definition of phase. By definition of phase, what you understand that the voltage or current through that conductor and the voltage and current through the other conductor sitting just adjacent to it are different. Then they are two different phases. That is the definition of phase. See, this and this. Next one are different phase. How we see, how we say. If they are having time displaced voltages and currents, that may be 20 degree apart also, that is also one phase. And even if they are if 5 degree apart, then also that is another phase, polyphase system like that. Okay. Understood my point, right? They need not be 120 degree apart for being called as a phase. You are used to, as an electrical engineer, you are used to three-phase system. That's why you think always in your mind 120 degree. Okay. But it is not true. You can also do 10 degree. That is also another phase, right? If two electrical signals are time displaced, that is a phase. They are different phases, right? So that's why we are calling it. So as you understand, the rotor will never observe similar phases in the adjacent slots because the magnet is only 2, but slots are 30. So 30 conductors will be facing 30 different phases, right? That's how we define the phases. Phases means they are not 120 degree always. Please understand. These are misconception. Phase means whenever the signals or voltages or currents are different in angle, in time angle, then only call it these are different phase. If they are same, we call it the same phase. Concurrent occurrence. If in the axis, if the time axis, there is a concurrence. That is when this signal is maximum, this signal is also maximum. Time concurrence. Do we call them as the co-phasor or same phase signals? But if they are maybe lagging or leading or having some angle displacement in time in their magnitude, then they are a different phase, right? That's why I define. Now we see a very important thing in rotating machine, which is the air gap, choice of air gap. So as you know, air gap is important for rotating machine because we don't want too much noise. See, air gap is important. Why? Because if you have a rotating body and a static body, they should be isolated, right? Otherwise, there will be friction. You have ball bearings and all those things in the rotor also to get out the tapping points. Just like bearings are important to connect static and rotating bodies. But still, you need some air gap, right? Some air gap. Why you need? Because without any air gap, even millimeter air gap or centimeter air gap, as you increase the power density, you need to introduce more air gap. And as you increase the speed also, you need to design the air gap. Once it is designed, it is designed. You cannot change continuously the air gap. But it is important for design of the machine. In induction machine, it is more important because air gap stores the coupling energy. So can you tell me a very important point? You learned about mutual coupling, right? Why voltages are generated? Because of mutual flux. Just like two coils, one linking other. The linking flux or the mutual flux will only create the coupling voltage or the induced voltage. Induced voltages are created only because of linking flux or mutual flux, not leakage flux. So can you tell me one thing? What is the leakage flux here in the induction machine? The flux going through the iron or the flux going through the air gap? What is the media between the rotor and stator for the coupling media? What is that? Air or iron? What is it? Rotor is here, stator is here. What is the media? Air gap or iron? Correct. So the mutual coupling is happening all in this air gap. So the complete energy is stored in the air gap and translated to that of the rotor whenever you use it as a motor, or the reverse way around from rotor to stator in the generator case. But all the air gap is happening, all the magic of electromechanical energy conversion is happening in the air gap. And how electromechanical energy conversion takes place? Through the coupling media. We discussed in the earlier week. And how is all the magic happening? By the induced voltages, right? By the flux linkages. From the mechanical side, you have the cutting fields and then you generate some voltages in the electrical domain. Or in the electrical domain, I am telling why iron is required. No, iron is required, not like that. Iron is also required. But I am telling you how it happens. Okay. So, iron is not required is not true. Because the former of the machine or the stator body, you need to have slots, right? To place the conductor. You cannot place the conductor on the air. So partly the flux will go through the iron body and then to the air and then link the rotor conductor and then back to the air and then to the iron of the former and then come to the slot and completing one loop like the magnetic field lines. Understood my point? So it has to go through iron. Agreed. But also it has to go through air to link the rotor conductor. Without linking, the coupling will not happen and the electromechanical energy conversion can never happen. So it has to go through air gap. So if it has to go through air gap also, we say the energy or the coupling energy is completely exchanged through the air gap. Therefore, the air gap has that energy or that power. Obviously, through magnetic media, we are doing the power exchange. But the air gap has the power. So can you tell me for the transformer and the induction machine, both has a magnetizing branch, and the magnetizing branch is nothing but a fictitious thing or a virtual thing which accounts for the coupling field or the induced voltages. Because we model it by a non-linear inductor. In this case, it is more or less linear because more or less it is air gap. So I can tell the non-linearity is much more in case of a transformer because of least presence of air gap. Because no air gap, right? In transformer, I told you, inductor you have air gap, but in transformer you don't have air gap because you don't need air gap because it is a static body, right? There is not an electromechanical energy conversion system. It is a machine, but electrical to electrical. But in induction you have air gap, and that's why the magnetizing path is more or less linear, but not completely linear because you have iron. You still have saturation effects, right? But compared to transformer, because it is completely magnetic, it is slightly less non-linear. Okay, but then you have air gap. And for air gap, we have the coupling energy being stored. So that's why the air gap power is very important, right? Air gap power. We encode this name, but this name actually you need to understand is coming from the coupling field concept. But can you tell me no armature reaction is being discussed in transformer and induction machine? Why? Yes. So up to this you understand, right? So air gap should be there. We cannot eliminate air gap. Okay, so now, but we never talked about armature reaction. In DC machine, armature reaction we talked about because there is armature reaction because it is a doubly excited machine, or even if it is a singly excited machine because of the field circuit getting energized and the armature circuit, two different circuits are there. So that's why we discussed armature reaction there. That okay, due to the armature current flowing, it just tries to oppose the flux, and we draw the characteristics also and discussed armature reaction. But I told you that for singly excited machine, we never discussed armature reaction. Why so? Similarly, if you go through any books, some good books on electrical machine, good books maybe some Langsdorff, Alexander Langsdorff, or maybe PC Krause. These books are very good books on electrical machine. Also given in the references in the course. So if you go through those books, you will just see, you will learn about these things, that why we are not talking about armature reaction in the singly excited machine. So can you think about why we are not talking about armature reaction? We know books, you can see that they are, but they will not explicitly mention the reason. But you have to understand, but that why for singly excited machine we are not talking about armature reaction. Can you tell me? Because transformer is a singly excited machine. Induction machine principle of operation is exactly the same as transformer. Just I will explain to you why. But still before that, try to tell me, because this point is important. Before that, try to address this point, then we'll go to that point, okay? That why its operation is same as induction or transformer. Air, no iron. What you try to tell? No. Transformer also there is no armature reaction. It is iron. Induction machine, although there is air plus iron, see, never think of induction machine as air. It is air plus iron, right? Magnetic field lines traverse both through iron and air. The rotor slot has iron, the stator slot has iron. How the path is completed? It is emanating from the stator, linking the rotor, coming back to the stator. It is air plus iron, not completely air. But still in both cases, we don't talk about armature reaction. Why so? And both are singly excited, right? Armature is in stator in DC. That doesn't create a difference. Whether you have armature in armature is not in stator in DC. Armature is in rotor in DC machine. Please see it once again. Armature is sitting in the rotor in the DC machine. In the all the AC machine, armature or the power circuit is sitting on the stator. But in the DC machine, armature or the power circuit, whenever tapping the power wires, right, they are sitting on the rotor itself. Armature is in the rotor of the DC machine, and for the AC, because of commutation, because you need commutation. But armature is sitting on the stator for AC machine. That doesn't create a big difference. Only why you kept the armature on the rotor in the DC machine, because you needed the mechanical rectification or the commutation. There is a completely different purpose. It has no relation with that thing, that why it does not have armature reaction. But what am I trying to address is that for singly excited machine, correct, one magnetic field, yes. So what? No. One magnetic field is also incorrect, because stator creates a magnetic field. For that, rotor creates, in reaction to that, rotor creates another magnetic field. So effectively, there are two magnetic fields working as per the principle of maybe double field rotation theory, maybe the principle of generalized rotation theory. There are two fields working together, okay. But in singly excited machines, you have one source which is creating the field, and in reaction to that, another field is getting generated, just like the transformer. So what happens? That field tries to oppose the main field cause and cancels it. Just like in transformer, what happens? Just let me draw and you will understand. You have the shunt path, right? I am modeling it as a simple inductance. And then you have the ideal conversion here. So till you have I2 equal to 0, there was only I0. That was very small in amount, because it was completely iron, right? The no load current I am telling, very small. When once you impress full voltage, because of very high permeability of the core, this inductance was too large. Because in transformer, this inductance was largest because of least presence of air gap. Why? Because the MMF required to create the number of flux for 100 volt, assume you have to create 100 flux lines. Why so? because d phi by dt. V is nothing but d phi dt. So once you impress 100 volt, almost 100 flux lines will come. Think like that. To create 100 flux lines through a very highly permeable media, you need very small amount of current. On the other hand, for induction, this current will be significant, 10 times, 12 times, 15 times, 20 times, like that, based on the design. This current will be significant higher because of the presence of air gap. The permeability changed, permeability reduced. To create 100 flux lines, still because of 100 volt being impressed in the primary winding or the stator winding or the induction, you still need to create 100 flux lines. But phi by reluctance is nothing but MMF. To create 100 flux lines, the reluctance is now lower. Sorry, reluctance is now higher for the air. To still create 100 flux lines, you need more MMF or more current. So this impedance will be lower for induction machine. This path, shunt path impedance will be lower for induction machine because it wants more current. So the no load current is higher because of the presence of air gap. So presence of air gap, XM is more in induction machine than transformer. But what we are talking about, that in reaction to that, as I2 comes, let's say I2 is 10, I1 will also be equivalently creating an MMF to oppose there by Lenz's law. And the two flux will cancel each other. Hope you understand what I am telling. Due to I2, I1 will come, right? Because I2 tries to oppose the main flux, and in reaction to that, the main winding or the primary winding pushes more current. That's the similar principle how induction machine works. Only the rotating form of transformer. Just you load it, slip will reduce, it will demand more current, the secondary current will increase. As the secondary current increases, primary pushes more current in reaction to that current. It is a coupling, 1:S, right? Just like transformer, only 1:S. Stator and rotor, they are primary and secondary. Both are dual of each other. So in reaction to the changing slip, the primary pushes more current and the MMFs cancel, and only the no load current, effectively no load current only is responsible for creation of flux. Because the primary current and secondary current MMFs are cancelling each other in reaction to Lenz's law. Reaction theory, basic reaction theory, right? So that's why we don't talk about armature reaction, because there is only one forcing function, which is creating the field and handling the power. And if in such cases, there will be armature cancellation, armature MMF cancellation, because it is working on reaction theory, right? And reaction theory works based on Lenz's law. And Lenz's law tells what? That it will cancel the main cause. There is no body or no circuit which is dedicated or maintained in order to generate that, or in order to keep that constant. If there were another circuit which we were maintaining or we were controlling, then we would have talked about the armature reaction, because then the flux would not have been completely eliminated. There would have been another flux which would have been disturbed by the current, and then we would have talked about armature reaction, right? Whether magnetizing or whether demagnetizing. But here, since the flux and the power handling stages are same, or the circuit is same, in reaction theory principle, the MMFs are getting cancelled. So we never talk about armature reaction, right? That's why. That's why. Same reason. Okay, so we don't have to talk about. Just read this. It is interesting that in induction machine, we actually try to design it with lower air gap. Lower air gap does not mean that no air gap. We try to keep the air gap lower compared to that in synchronous machine. Why we will discuss in the synchronous machine. But for the time being, please understand that compared to synchronous machine of similar rating, induction machines are having lower amount of air gap, because we don't want to lose flux. More flux we want and more torque we want. See, air gap is the coupling media. Understood. But if you increase the air gap between the stator and rotor too much, more leakage will happen. Agreed or not? The stator will push flux. Some flux will link rotor, but more of the flux will not link rotor. So we lose something. We want all of the flux to be linked with the rotor. Till the time it is not linking with the rotor, the flux getting in the air gap does not guarantee that it is a mutual flux. the flux should get in the air gap and link with the rotor. Now, if we increase the distance between stator and rotor too much, some flux will come and not link the rotor. That we don't want, because if it is so, then the coupling field strength reduces. Why? Because if less flux cuts the rotor, less voltage induced. Less voltage induced means less torque, because the rotor's magnet strength reduces. And if the magnet strength reduces, less torque will be there, because torque depends on strength of the magnet and the angle between them. Think like that. So if the less linkage flux, less mutual flux being linked and more flux getting leaked, in such scenario the magnet strength of the rotor will reduce, which will result in lesser strength of rotor magnet as you increase air gap. So what we do? Air gap increase, leakage increase, rotor strength, rotor magnet strength reduce, torque reduced for same machine. Do you want that? Do you want that for same machine you are losing flux? No. So that's why you don't. But please understand that does not mean we keep it zero. Keeping it zero has other mechanical consequences like more noise, more friction and windage loss. We keep bearings. There are bearings, because also we want to take the shaft out. So there will be some coupling between static and rotating body. We have bearings. But still there is air gap. Air gap is necessary because you cannot completely just push to the stator. There will be high friction, right? You don't want it. And also you need to process the process the torque, right? So for that you need to have actually cannot make it zero or cannot make it completely large. Then you cannot get torque. So both sides you have constraints, right? That's how. But please understand that if you keep too high air gap, then torque will be compromised for the same machine. We don't want that. And power transfer will be compromised because you lose flux. And if you lose flux, you are in a way losing power transfer. So how much ever power you are giving, that is not coming out. So you are compromising on the electromechanical energy conversion. So we don't want to compromise on electromechanical energy conversion. So that is a way, design principle. That is a design principle, but mechanical constraints are also there, that we cannot too much increase the friction and windage losses. So phasor diagram, as you told, it will be just following the transformers, just like the transformer. That the flux will have the lagging voltage induced, and that will create the currents in the rotor. The rotor flux and the stator flux will try to oppose each other, but not completely, because you have the no load current. And the no load current you have, and the sum of two will generate the, for a given load, you just take the load how you want the load, and that will depend on the slip. So based on an optimal slip, you can draw the phasor diagram, and that will be opposite in nature. They are opposing because of the reason of the Lenz law, right? Just like that. And just Vt minus IARA minus IAXS, same, or ISLS will give you Vs based on the operation of the like a motor, right? Or a generator. You can draw it for both. So generally we draw it for a motor, right? That we apply the voltage and we get the field, and from the field we draw the induced voltage in the rotor, transferred to the stator, because this is all transferred to stator. So do you know why this R2 by S comes in the equivalent circuit? Because your S times E will be a voltage induced in the rotor, and you have some R2 and SX, slip times frequency, right? So once you take it to the stator, this will be, the voltage will be 1 by S times. So the EMFs will be same, referred to stator. So you can couple the two circuits. So after this is the rotor circuit, and referred to stator, and this much is the stator circuit. So to couple the two, you need a common voltage by network theory. And how it can do? We can just shift the secondary voltage, which is S times E away. So 1 by S, and then operating frequency also changes. Please note operating frequency is changing. That's why 1 by S times only. But 1 by S times and then turn square if you have doubly wound. But we don't have it, so that's why 1 by S, right? And then R2 by S. But remember R2 dash by S. This is hidden. This people don't write. People consider it for granted that it is 1:1, but it is not so. By transformer principle, 1 by turn square will be there. But that they don't write it. But 1 by S should be there because frequency is changing, right? Rotor and stator circuit coupling can only happen once you make it to the same frequency. Similarly, phasor diagram also you can draw. Phasor happens in same frequency. Otherwise, you cannot draw phasor diagram. Also, two different circuits you cannot couple if they are of different frequency. So all the things need to be taken to the stator, and once you take all the things to the stator and reflect R2 dash and R2, they tell it like that, but actually it is R2 dash since you are reflecting to the stator. And for doubly wound, we are talking about squirrel cage, but for doubly wound there are some turns ratio also. So once you take everything to the stator and I tell you the rotor resistance, to bring it with respect to the stator, you have to divide by turn square. So that's how we do it actually. It will be given, but if it is not given, 1 by turn square and then 1 by S. 1 by S is coming for a different reason. Please understand, because of the coupling of the stator and rotor. And then turn square to bring it from rotor side to stator. If 1:1, no issue. If it is 1:1 turns ratio, like in so 1:S for voltage transformation, not turns ratio. So turns ratio will be 1 by N square. So please don't confuse, okay? Just to bring you the equivalence of the two operation with transformer, we are writing like 1:S for voltage transformation. Obviously, voltage transformation is slip times. But for the parameters R, X, and all those things, their X is both frequency dependent as well as your turns ratio dependent when you take it to the stator. So 1 by S, why we did? 1 by S we did because of the reason that the frequency is changing. See, frequency to stator frequency. That's why here it became X. So what I was telling, just for the time being, neglect the stator part and think that with the stator applied voltage is impressed across the rotor circuit reflected to the stator side. So what you get? I2 square R2 by S. This is the complete power coming to the rotor. But what for is the torque generated? Torque is generated due to air gap power. Yes or no? After the stator copper loss, whatever power, active power is there, that is responsible for generation of the torque. Okay. So what is I2? I2 is V by, yes, R2 by S whole square plus X2 whole square whole root over. This is I whole square into R2 by S. Right? But this is what? This is power. So I need to also divide the power by what? This power should be equal to torque into omega. Now what should be this omega? Omega R or omega S? I took the air gap power, remember. This will not be omega R. If it was omega R, I needed to take I needed to split this R2 into R2 and 1 minus S by S times R2. R2 plus R2 by S into 1 minus S. I can write like this. So this part goes into copper loss of rotor. And this part goes into mechanical power conversion. But I did not take this part. R2 by S into 1 minus S factor I did not take. I took here R2. Actually, I would have taken 1 minus S. Should have taken 1 minus S. To write this as omega R. Yes or no? Actually, mechanical power is coming for what? For mechanical power. Torque into omega R is mechanical power. But did I take R2 by into 1 minus S here? Yes or no? No, right? Either I would have taken torque into omega R. Don't confuse, you are completely blundering it. No, it is not the reason that there is no mechanical loss. It is for the reason that there is copper loss. I need, if I write torque into omega R, that is mechanical power, okay? What should it be equal to? It should be equal to mechanical power. But the R2 by S is not mechanical, it is air gap. So I needed to have written R2 by S whole square plus X2 square V square by this into R2 by S into 1 minus S, because this is mechanical power, not R2 by S. So if you take this 1 by S this side, it becomes torque into omega R by 1 minus S. And what is omega R into 1 minus S? Sorry, omega S into 1 minus S. Is it nothing but omega R? So omega R by 1 minus S is nothing but omega S. So either you write tau into omega S equal to this. So in this case, you don't take omega R. If you don't take omega R and write here omega S, then you should not write 1 minus S here. Or you write omega R here and take 1 minus S here, because you are equating the mechanical power. But generally in books you will find they are taking as torque, they are writing torque as 1 by omega S times V square by R2 by S whole square plus X2 square into R2 by S. Generally they write like this. Or they also write like R2 square plus SX2 whole square, and then they take the S here, and then the S square was up, and then S square and R2 by S cancels. So S V2 square into R2 by R2 square plus X2 square. Many SX2 whole square. Many forms are there. And now if you use Desmos, you try a graph plotter and you get a function like this, some form of function like S by maybe X by 1 plus X square. You just plot X by 1 plus X square and try to plot it with respect to X. You will get a graph like this, right? So that's why like this. And you try to differentiate it and try to calculate the maximum torque condition, slip at which maximum torque to get R2 by X2 approximately using this approximate circuit. So this is an approximate circuit. Many books use it and it is valid. Okay, the approximate circuit is valid for calculation, for easier calculations, right? So you get R2 by X2. For that, you get the maximum slip at which maximum torque occurs. And we go to the important relations and formulas, which are already you know that the power you must have seen in the lecture also. So I will not press upon those much, but you need to know that I can split R2 in two parts. Sorry, rotor resistance RR or R2, as R2 by S was there, so I can split it as R2 plus R2 by into 1 minus S by S. This part I call mechanical, and this part I call rotor loss. But loss is also happening in stator, right? But after the stator loss, whatever electrical power is coming is known as the air gap power. And these are losses. That's how the equation is developed, right? And this is the Thevenin equivalent, right? You take the Xm and the Rs and Xs and merge as a Thevenin equivalent model. So the V Thevenin and R Thevenin X Thevenin will come. Or you can neglect the XM, which is not correct. But for simplification, you must have learned that you can neglect XM and then directly consider V Thevenin to be V source and can plug with the rotor circuit. Just now we did that. Okay, in BTech we can do like that. But it is not true, not correct. Because why it is not correct? If it was transformer, it would have been correct. Because stator coil leakage and resistance is too low, we can neglect that. And XM is too high. But XM is not too high for induction machine. So do not neglect XM. XM is lower. So you cannot be neglected, right? If it was too high, it can be open circuit neglected, right? Like network theory. But here we consider the Thevenin equivalent model. They will be given. So in simplification of the model, we give R1 and X1 as Thevenin series parameters. And then you can connect your V source with that. You can just assume it to be almost equal to the source voltage. So that will be specified if you need to take anything else, right? And you know the dependencies with sleep. Just I plotted one thing, interesting parameter. So power factor you can calculate as R2 by S divided by R2 by S whole square plus X2 square whole root over. Similarly, you plot it and you will find one thing, that it behaves like maybe 1 by 1 plus S square, sleep square. But sleep you cannot take. Sleep is actually when speed increases, sleep decreases. But see, if you plot it, so if sleep, because sleep is within 0 to 1, right? So ideally, mathematically, as speed increases or sleep increases, this direction if I go, my speed is increasing, so sleep is reducing, and I am getting good power factor. So as I increase the sleep, as I increase the speed for a given load, if I increase the speed, my power factor improves. That is also understandable because at no load, the sleep, what is the sleep at no load? Can anyone tell me? What is the sleep at no load? At no load, machine almost rotates close to synchronous speed. So what is sleep? Almost zero at no load. At no load, I am telling. At no load. At no load, the machine, not at starting. I am at starting, sleep is 1. At no load, sleep is almost 0. If the machine is moving, rotating, it is almost rotating as close to synchronous speed because it is not loaded. So at no load, it is almost close to 0. So the machine power factor is not that great. What I am trying to tell. Why can you tell? Because this curve will not be like this. This curve will be like this. Because practically what happens, once the machine reaches the synchronous speed, the power conversion will stop. Hope you understand. So there will be one point like this. After that, it will just fall. And also you know that if there is no active power being transferred at no load, and there is only the reactive branch, then also the power factor will be poor, right? So both ways you can tell that the power factor is poor. If the machine is not loaded or not handling. But if the machine is loaded also too much, then also sleep will be reduced, and as sleep reduces, power factor is not that great. So both ways you have some constraints, but more constraint on the sleep getting very low. If sleep is very low, then it is almost reaching the synchronous speed, then the power conversion will stop because of Lenz's law, because you are not getting good torque. That is also dependent, right? So a power factor curve is almost looking like this. Understood? And Just look in this region, up to this region, optimal sleep, and then up to full load sleep maybe. Generally when sleep, you are increasing the speed, your power factor is improving. And if you are decreasing the speed, your power factor is reducing. So this is for a given speed. So for a given load, for a fixed load, you change the sleep and see what is happening. Don't change the load. If you increase the load, the power factor will improve. So don't try to play with both things. You keep the load fixed and change the sleep. Then you will find that on slightly reducing the sleep, the power factor is improving. But not much. If you take it too low for a given load, then the power conversion will stop. Because at synchronous speed, you know, the EMF induced in the rotor will be 0 and hence power conversion will stop, as you will not get torque. Understood or not? This curve is understandable, I think. So this is actual, this is mathematical, right? This is mathematical. See, load increased, power factor decreased. Don't try to see like that. For a given slip, if you try to increase the load, for a given slip means even if you increase the load, speed will try to decrease. But by some arrangement, you try to maintain the same speed and you increase the load. Means you are increasing the active power conversion. Then your power factor will not decrease. Then your power factor will improve. So don't try to play with both things. From no load to full load, if you maintain a fixed speed, your power factor surely will improve. Because at no load, active power was 0. At full load, active power was more. At no load, there was reactive power, Vm by Xm, Vm square by Xm. At full load also same reactive power, but active power increased. But sleep did not change. Since you maintained the same sleep, then your power factor will be more, improved. But I am telling for a given load, you are not changing the load and you are playing with the sleep or you are playing with the speed. Then for a lower value of sleep, your power factor will be more for a given load, not changing the load. You understand my point? That is that both things are different, right? Obviously, if we load the machine, the power factor should improve for a given speed if the speed is maintained constant. But generally, the speed don't maintain constant, right? For an open loop induction machine. So that's how it is intuitive, right? So now we go to some numericals. Numericals are very easy for induction machine. You just need to play with the circuits, right? So I have some few numericals for you. So that see, for a low sleep, it is asking the torque. So you know how to do it. It is asking low sleep. So which term will dominate? Which term will dominate? So low sleep means this term is very high. And also this term is very high compared to this term. So neglect x2. So v square by r2 by s whole square into r2 by s. What is it? It is coming, a square is coming on top. And so it is proportional to s. So this one is correct. So at low sleep, it is coming proportional to sleep. So how the torque versus sleep characteristics looks like? This is high sleep, this is low sleep, right? So at low sleep, as you increase sleep, it is almost linear. And for high sleep, you will find it is 1 by s, right? So I like this. As sleep, maybe what I can tell, as sleep in this region, as slip increases, torque reduces. So 1 by S. And you merge the both, you get these characteristics. Understand? This is understandable, right? So not much difficult. Similarly, slip at which maximum torque occurs do not depend on voltage or magnitude of the peak torque depends on voltage. True or false? True. Because what we told, magnitude of torque is depending on voltage, right? But slip at which maximum torque occurs does not depend on voltage. It is R2 by X2. So this statement is true. Similarly, if rotor resistance increase to bring torque at, so what we do like this, that we increase rotor resistance. For a same value of voltage, you get different peak torques, right? So, but your slip at which maximum torque occurs will change, right? Maybe like this. But the value will be same. Because you are only playing with the increasing resistance, but voltage is still same, right? So maybe like this, right? So what it is asking, rotor resistance is increased to bring peak torque at starting. Then for that rated torque, current at starting is rated. Obviously true. Because if you increase the torque at starting to the peak torque, then for producing that peak torque, current will also be maximum, right? Because what is torque? Torque is come by, if you try to balance the power, in order to produce such a torque at starting, it should take more current, more active component of current plus the no load current. So the current also increases, right? So it is nothing like that at starting current will be low or high. It depends all on the resistance or the starting torque that the characteristics is demanding. So by the characteristics, if you try to push more torque at the starting by the design, then it will take more current to build that torque. Quite intuitive, right? So it all depends on the characteristics. It is possible that you try to bring the characteristics or shift the characteristics or the peak torque at the starting, right? But please understand that the peak torque magnitude will not change. But it's changing its position because the slip at which maximum torque occurs is changing with varying resistances. Similarly, the torque speed characteristics can be made linear. So torque speed characteristics can be made linear. So like this, they are asking like this. So you can shift the characteristics to the starting. So this part is linear, right? By increasing external resistance. So this is a kind of fill in the blanks. And I told you mutual inductance is defined not only by the strength. Strength of the currents defines the saturation. Saturation can change the material property because the mu changes. I told you in the previous week. And once the mu changes, the material property changes, the permeance changes, and hence the mutual inductance also changes. So mutual inductance is not only dependent on the space parameters, which is the dimensions or the number of turns, because mutual inductance defines on the number of turns of the two coils, N1, N2 with derived, right? But it also depends on somehow the current also, because the permeance is also important of the coupling media. And the permeance is itself governed by the currents. We saw, na? Currents changes the saturation, and then once it is saturated, mu reduces or increases. We saw with saturation, mu reduces, becomes like air gap. So mutual inductance or inductance not only depend on the core properties but also on the current that the coils are bearing. Coil property, coil turns, it depends, number of turns, core material property, but core material property depend on the current of the coil. Because once saturated, the core material property behaves like air gap. So it both depends on space and time. So space, not time, is not true. Depends on both space and partly on time. Time means current parameters, right? Because current parameters changes saturation, saturation changes mu, and mu changes mutual inductance. So please give it a thought upon, okay? So similarly, maximum torque under running condition. So you can just check what is the magnitude, and you can see that it is inversely proportional to the rotor reactance that stands still, because it is R2 by X2. So maximum torque. Once you plug it in, so plug SMT as R2 by X2 in the torque equation. and you can see that it is getting proportional to 1 by x2. So just check, okay? You can just check it. And the stable operating region. What is the stable operating region? Maybe a load torque like this, and this is the electrical torque. So stable operating region is which side? No. Which side? It has two intersections, right? So T should be equal to TL, right? For stable operation. Now it has two intersection points. So which point should I take? What is the stable point? In this point, if I place on this point, so if my load torque increases, or think it in a different way, so in this side speed reduces and speed increases this side. So see, if your intersection point, you take this point, you think that this point is stable, just check. If your speed increases and you are operating at a particular slip, so what will happen? Your electrical torque is more and your load torque is less. So if speed increases, electrical torque is more, but load torque is constant. What will happen? Speed will further increase. Understood? If it is considered as a stable operating point and it slightly speed increases, then T increases. It will ramp up. The speed will increase because T is more, right, in this section. So it is not a stable region. Now go to this side. If speed further tries to increase, then TE reduces. But TL is constant. So speed reduces because TE less than TL. So once speed increased, torque reduced, so speed reduced. And once speed reduced, because this side speed is reducing, the torque increased. So it again brought back the speed to the stable zone. So a stable point should be having such a characteristics that even if it deviates about it, the electrical or the load torque will bring it back to that point. So this zone is the stable zone. The high speed running zone is the stable zone, not the starting path where you have this kind of characteristics. So always the stable operating zone is this side, the high speed side or the close to synchronous speed side. That's why our induction machine always rotates very close to synchronous speed, right? Hope you understand the points. And the number of rotor phases in a squirrel cage induction machine, I told you, is nothing but number of slots, rotor slots per pole. Hope you remember, right? So this is also one question. And then we have few problems, very easy problems that we have been given as the percentage of losses. So once you are dealing with a motor, always induction motor, if some power is given, that is the output power, output mechanical power, not the input electrical power. Always when some power is being specified in a motor, it is the output power. For a generator, it is also the output power but electrical. So please take into consideration, this is the mechanical output power. So accordingly you calculate the slip and the rated windage and friction loss, you can calculate 1% of the rating. But mechanical power developed is you can calculate because friction and windage loss is there. So this is the PM, right? Because generally when we write that I2 square R2 by S into 1 minus S, this is the developed mechanical power. But actual mechanical power, so this is developed mechanical power, developed PMEC. But actual mechanical power is little lower because we have the friction and windage loss. So we need to add back that friction and windage loss to get the developed mechanical power. Why? Because from that only we can calculate the slip. 1 minus S you will divide to get the air gap power. But that you can only do with the developed mechanical power, not the actual mechanical power. Because developed mechanical power will also go through one more stage, which is the friction and windage loss. So that's why we added and then got back the developed mechanical power, which is a slightly higher than the actual mechanical power. and then we can divide 1 minus s, and then we can calculate. So 1 minus s as sleep, how we calculated? Just by the synchronous speed RPM and then the operating speed 960 RPM, and then we got the sleep. Once we got the sleep, we can derive the air gap power. Air gap power is nothing but the input to the rotor, the power input to the rotor, and then the rotor will suffer the copper losses, and then it will develop the mechanical power. But another stage it will go, that the friction and windage loss, and then will the output. So the stage is like this: air gap. So the power will come, electrical power will come like this, and then the stator copper losses will go away, and then the air gap power will come, and then the rotor copper losses will go away, and then the developed mechanical power, and then I will take out the friction windage, and then the PMM actual. So this is the power flow diagram. Power flow. And accordingly you can calculate, right? Similarly, you can just, if everything is given R1, R2, X1, X2, XM, so you need to calculate based on the actual model, right? So they are only giving XM, so many times they give RM also. So take a shunt path and then you calculate. So R2 by AS, X2, R1, X1, XM, everything they are giving. So accordingly you just do network theory, right? You have some VM and you calculate the Z, and then from that you can get the air gap power. Air gap power is nothing but I2 square R2 by S. So calculate I2, this is I0, this is I1, I2 square R2 by S. Or they call it I1 also. So you do all the thing and you take the current, whatever current you get entering into this path. What you can also calculate separately, or you can calculate as a lumped parameter. So what I have done what? R2 by S plus JX2. So this is, I am taking parallel, and then I'm trying to calculate the current, right? This current. Then if it is actually, I need to take the complete total magnitude of current, and for that I'm trying to take the equivalent impedance, and then I can calculate the current, right? So generally, after the stator copper losses, after the R1 and X1, I can take I1. So I1 and I2 are only coming different because of I0, right? But I need to consider I0, and if I consider I0, then it will be I1 square, considering XM, because that we neglected in the previous analysis, but that should not be neglected. So actual current square into R2 by S gives the air gap power, right? So actually, if you try to calculate I1 square R2 by S considering XM, and without XM, I1, I2 both are same. Without XM, I1, I2 are same. So accordingly, both are same. So this is coming by power balance, I2 square R2 by S. That is I1 square R2 by S if you have XM, because this is the current here. Both current needs to be taken into consideration, right? Similarly here, total current you calculate. So I1 and I2 dash may be synchronously written, right? They are all same. I1 is I2 dash plus I0, and then you can calculate. Same circuit, right? So this is called I1, then I0 will go here, then I2 dash. If I0 is considered, then I1 is I0 plus I2 dash. And all the analysis will go from I1. But if I0 is not there, not specified XM, then I1 and I2 dash are same. So if they have specified XM, don't neglect that and consider it, and then do all the analysis, not with I2 dash, but with I1. Other things you have, so we do per phase analysis, right? So line current should be √3 times, because if it's star connected, √3 times I phase. This circuit was per phase circuit, right? Equivalent circuit, whatever we discussed, this is a per phase circuit. So if it is star connected, you know, line current and phase current are same. If it is delta connected, if delta, line current is √3 times I phase, so that's why √3. because up to this was per phase analysis. Likewise, okay. Let's go through the problems. And I already told you the frequency of rotor is nothing but the slip frequency of the stator. Slip frequency, that is slip times frequency of stator. And you calculate slip and multiply it by stator frequency, that will be nothing but the frequency of voltages and currents induced in the rotor. So I calculate how much is that. Slip you calculate, and then pole pair. Total number of pole you calculate synchronous speed, and you know the operating speed, you calculate the slip. Slip times the stator frequency, 50 Hertz, will give you rotor frequency. So rotor frequency is a slip dependent term, and you calculate slip based on the speed of the machine. And once you have the slip, you can calculate the rotor frequency. Slip times stator frequency is the rotor frequency. So you calculate 1.33 Hertz, right? So they are very easy problem. Once you go through, you will understand, right? Please go through them. It's same the starting current. For starting current, please put S equal to 1. In the overall R2 by S, just S put 1 and then try to calculate the starting current. Calculate just simple network theory, that how to calculate the parallel and series combination of the net impedance and then net voltage divided by current, impedance per phase analysis. And then if it is star, you know phase and line currents are same, and you calculate and you just take its magnitude. That will give you the starting current. Only it is little calculated. Sometimes to make it simple, we can also remove XM. Problem becomes then very easy. Otherwise, with XM also try once. Try to calculate fast, because these calculations will take your time. So learn how to do it fast, like, because there are 10, so it should be easy, right? And just do the square root, that a square plus b square whole root over, to take the magnitude. Know how to do from Cartesian to polar, right? And then a small amount of single phase induction machine also will touch. You know that in single phase you have a pulsating field. So you can break a pulsating field into forward and reverse fields, right? And there are 3 types. You must have gone to the lecture. There's split phase, capacitor start, capacitor run, or shaded pole machine. The idea is to actually know that since the field is pulsating in nature, you need to have some mechanism to start it, right? Sorry, let me plug in. You should have some mechanism to start, because at starting the torque is 0. Because the forward and reverse torque or fields are equal and opposite. So a pulsating field, if you break into forward and reverse paths, their strengths are equal, and for that reason they don't produce any starting torque, net starting torque. Net starting torque becomes 0. That is undesirable, right? That story I wrote, that the two field revolving theory, you can break, but at starting you don't get any torque. So that's why we plug in another winding and try to create a phase shift and try to create maybe two phase displaced fields just for a momentary time, for some time, and then the forward field will develop more strength once started. At starting, both are equal and opposite. That's why we cannot start simply by automation like in the induction. Induction machine is self-starting, right? But in this kind of fields, single phase, the magnetic field is actually pulsating in nature for the single phase nature of the currents, and that's why we cannot start it, because the net starting torque is 0, and for that we need some starting arrangement by some another field excitation, right? To actually rotate the coil, rotate the rotor, to give some forms of field by some phase displacement. So capacitor we use actually to create a displacement between the two fields, and then once that starts, some speed comes, then I will prove or show you that the forward field strength is more than the backward field strength, and we get a smooth torque. But please understand that these forward field and backward field are also speed dependent terms, unlike that in the 3-phase induction machine. In the 3-phase induction machine, the net magnetic field strength was fixed irrespective of the speed of the machine or the sleep of the machine. But here they are sleep dependent terms. So as you see here, if you go through the derivation, I broke the field which is constant, or I can say which is pulsating with time but not rotating in space. It is only fluctuating. So if I break it, I will get two rotating magnetic fields which are rotating in opposite direction at starting. This can be also proved by the Euler identity, where you get two different rotating magnetic fields in the opposite direction. So one I call the forward, one I call the backward. But at starting, you see both are having equal and opposite strengths. But once you rotate it by some arrangement, then you see the forward is developing more strength and the backward is developing lesser strength. The torque, I am telling. Why so? Because the forward field develops the strength based on the slip and the backward field is 2 minus s. So due to the significant 2 minus s turn, as speed increases, the slip reduces and 2 minus s is dominant. So 2 minus s slip for the backward field induces much larger voltage and poor power factor currents because R2 by 2 minus s is lower power factor than R2 by S. The R2 by S is much higher, much dominant, so better power factor. So forward field power factor is more, better, and R2 by 2 minus S, the backward field power factor is lower, and its strength, the R2 by 2 minus S, induced EMF and current strength is higher, so the opposition to that field is more, and its dominance is lesser as the speed increases. So as speed increases, slip reduces, forward field strength is more than backward field. So that's why we started using some mechanism, some forms of displacement between the two. We try to create some two fields, some field space displacement between the two fields so that I can start the machine by some RMFs, by two fields, some angle difference, and I create some moving magnets, some form, and I can start it, and then I showed you that with slip, these field strengths actually vary as the speed varies, and once I catch the close to the synchronous speed, the forward field dominates, and then I don't need a starting arrangement. I can just remove that starting arrangement which I created using the space displacement to create the rotating magnetic field. Otherwise the field would have been pulsating and I did not get a starting torque. That is the arrangement we follow, and equivalently you can go through the derivation of the two field theory, and this is how we cut during the transition. When I don't need, I can open the auxiliary winding. Why? What was the purpose of the auxiliary winding? To create the RMF. Once I started, because the starting torque was 0, once I started and I reached almost close to the synchronous speed and the dominance of the forward field is started because of the slow sleep and the 2 minus s term is the backward field is getting more opposition and hence the backward torque is low and the forward field torque is more, then I can open. Already the forward field is more, torque is more, right? So I don't need an external arrangement of the auxiliary winding. I open it. Also more variants are observed, like the capacitor start and capacitor run. Both all types of single phase induction machines are, all variants exist, right? So this is the, but the always remember the auxiliary arrangement was for the starting, right? To create the RMF, because otherwise the field would have been pulsating, and I broke it and showed you that the forward and backward field strengths were equal, and then they would not have created a starting torque. So starting mechanism, for that we created the auxiliary, but for the space, for the angle displacement, the time displacement, or the phase displacement between the two, I plugged in a capacitor, right? So that would have created, and also you know that the auxiliary winding is designed with higher resistance and lower reactance than the main winding. This is also to create the angle difference, right? And equivalently, I have two circuits, the main and auxiliary, and each has its own forward and backward resolution, because both are single phase coils in their own terms, and I can break them into forward and backward fields. The forward field has 2 minus s and the backward field has s, 1 by s. But please understand that one thing, So forward branch and backward branch I resolve, but both are connected in parallel. That's why V1 and V1. And the auxiliary and main winding has a turns ratio A. So that's why A square reflected to the main, right? So this is the equivalent circuit similar to that of the induction, but resolved into forward and backward field, because this is a single phase, right? And just go through it, because I'm not covering it much because it has been well explained in the lectures also. And the analysis will be similar to that of the three phase, but in superposition of the forward and backward field, right? And how to determine the auxiliary and main parameter along with the shunt parameter. You do the no load and block rotor test. You energize the auxiliary winding and keep the main winding open and try to do the block rotor test. Why we do block rotor test? Block rotor test is done to find the series parameter, and to do the and to determine the shunt parameter, the XM, you do the no load test, right? So series test and shunt test I can do with block rotor and no load test. But no load test only for one you can do. You can de-energize one of the coils and then can do the no load test. Anyone. You either energize the main or the auxiliary. Don't energize both together. You can also energize both together. Then you have to consider both. Okay. Otherwise, you have to energize only one of the coil. That will simplify the calculation. And individually for the series, using the block rotor, you have to do 2 times. One for finding the parameter of the auxiliary and auxiliary series parameter, the resistance and the leakage, and one for the main, the series parameter. Otherwise, it is all the same. So, and the rotor parameters you will always determine from the block rotor test, right? And this term, you already know H2 and R2 value from the block rotor test. You can plug those in and can calculate the no load test and can do the no load test for calculating XM. So XM actually we calculate using the no load test, similar to that of the transformer, but with varying this R2, this dominance of R2 minus S and R2 by S terms and R2 by 2 minus S. 2 terms are there. So just see what will dominate. That in block rotor test you have high slip, and for high slip that R2 by 2S, this term will be 1 at block rotor at standstill. So these terms are dominating, right? Because you have higher slip and lower impedance, right? These are low and this is high, almost higher. So it can be neglected. And you get these parameters, series plus rotor parameters. Using block rotor test. But you need to do it 2 times. Main plus auxiliary. So this is the main, this is the auxiliary. So accordingly we do it, and you have some problems that what is the capacitance value you can calculate by first determining what is the angle displacement initially and what is the angle displacement after connecting the capacitor. You need 90 degree. From that information you can calculate the capacitor value. So just go through the problems. I will include the problems and how to calculate the torque. So I told you the torque is dependent on the strength of the currents and the angle between them, right? Or the strength of the magnets and the angle between them. Similarly, the strength of the currents and the angle between them, because the voltage is same. So accordingly we do it. And similarly for the auxiliary winding, how to calculate the capacitor value. All I will include in the material. You can see and go through the problem. And with this, I want to end the lecture because already we are going above the time. So please go through the problem, and if there are any doubts, you practice and solve it. And if there are any doubts, you can just let me know. Okay. So I end the session here. Thank you.